Hello, I'm Eugene, and today I'm going to go take a look at 1 to 102 Sprint 29. Hey, it's a standard range problem for a rational function, something very familiar for IM3 and Algebra 2. What could possibly go wrong? Oh, and terms are factorable too. Factor, factor, factor. Deal with the negative exponent. Factor, factor, factor. Oh, and terms can cancel each other out too. So then we have a numerator of 1, a denominator of whatever that is, and a domain restriction where x cannot have an input of 1. Now it's time to think about what the graph would probably look like. So vertical asymptotes at x at equals 2, -2, or 0, because that will make the denominator 0, resulting in an output undefined. Horizontal asymptote at y equals 0, numerator is a constant, denominator is a polynomial term. As x goes out to infinity, denominator is going to go way out larger than a teeny tiny constant, and thus it will approach 0. And also there's going to be no x-intercepts because the numerator is a non-zero constant. And with that, we can do a sketch of our function. By the way, technically there's a hole at x equals 1, but in the end, it doesn't really matter that much for the range, because if you expand out some of the terms in the denominator, all the exponents of x are going to be even. That's going to indicate symmetry between the y-axis, and that would mean that f of -1 is going to equal f of 1 without the restriction. And so let's think about as x goes to way out to a positive infinity, it's going to approach 0. But if we go all the way back and approach 2 from the positive side, denominator is going to approach 0, and the output is going to skyrocket. And all positives are going to be covered. Negatives, it's going to be a different case. So we go from negative infinity, but we go all the way up, but only to a certain point. Since we don't even reach the x-axis, there's no x-intercepts, and then we go all the way back down. And it's definitely going to be important to figure out what this local max is going to be. And that's where we can use our graphing calculator. Hold on, wait a minute. Where's my graphing calculator? Uh-oh, I left my graphing calculator in another room, which means I can't even use it, and not that it matters anyway, because Sprint bans graphing calculators. So we're going to have to use a different strategy. Oh wait, there's calculus. This is a continuous function. If we take the derivative, which is like the tangent line, and then set it to equal 0, that's where we can find our local mins and maxes in those critical points. Except this is a Math League test. Math League says we can solve all these problems without having to use calculus. So there's got to be a way to solve this problem without a graphing calculator and without calculus. What other strategies are there? Time to think about what the denominator is going to output. So 1 over x to the 4th times x squared minus 4. That's going to be less than or equal to some negative number. And then if we rearrange it, multiplying both sides by x to the 4th times x squared minus 4 at the negative range, and then divide both sides by -n, which result in 2 swapping of inequality signs, then we get something in the likes of this. And multiply both sides by -1 to get this. Hey, there's some x squared terms in this mix. Maybe we can use some substitution where k equals x squared. And then we can get -1 over n is greater than or equal to k squared times 4 minus k. But that's a cubic. Well, there goes that my thought of being able to use quadratic minimization strats or maximization strats. It's got to be a different strategy. I know I heard some people talking about a surprise tool that can help us later in this problem, and I think I wrote it in a sticky note behind me, so I'm gonna go take a look on what that is. Wait, this thing. This little thing, that's the AMGM inequality. I think some of you may have heard about the 2 case before, but there's also the 3 case and technically a bunch of the n case too. But I wonder how would that help us? I mean, there's a k squared, and then, but we have k times k. But wait, if we do k over 2, then you add them together. Hold on. If we do k over 2 plus k over 2 plus 4 minus k, by the AMGM, that will be greater than or equal to the cube root of k squared over 4 times 4 minus k. All right, then we can do some simplification to get 4/3 is greater than or equal to the cube root of all that. And then we can do some even more rearranging to get 256 over 27 is greater than or equal to all that. Ooh, that's very useful. And then going all the way back, we can get that in the negative case where where we're going from 0 to 2 or -2 to 0, we get x to the 4th, 1 over x to the 4th times x squared minus 4th. That's going to be less than or equal to -27 over 256. The AMGM also has an equality case where if k over 2 equals k over 2 equals 4 minus k, then you get that equality, which basically means that the equality case can happen. In fact, I can even show you that, since k over 2 equals 4 minus k, that would be k equals 8 over 3. And since k equals x squared, we get x equals the square root of that, which is going to be less than 2, since 8 over 3 is less than 4. All right. And with that, we can finally say what our range is going to be. In interval notation, of course, going from -infinity all the way up to -27 over 256 with a bracket, and then union with 0, not including 0 since there's no x-intercepts, all the way to positive infinity. Whew, and we're done. Yeah. When we get rid of the graphing calculator, a standard problem can be so much harder than it seems.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.